Our next speaker is Marsh Cuttino, Dr. Marsh Cuttino. I first met Marsh, I think, at a suborbital researchers conference, or maybe it was New Worlds, I forget. But Marsh has a BS in chemistry from James Madison University. He's apparently a Virginia guy, got his MD from Virginia Commonwealth University School of Medicine. He's currently a emergency physician for Team Health. And he's also the founder and CEO of a company called Orbital Medicine, Inc. So he definitely fits right in here. He's an FAA aviation senior medical examiner. He's going to talk about his experience as one of his other many hats, apparently, a flight surgeon for the Zero-G Corporation. And he's not going to be talking about intracranial pressure, measuring it by looking at eyeballs. Fascinating topic as that may be. Marsh?
All right, can I get an audio check? Thumbs up, Rand, if you can hear me.
Yep.
All right, very good. So as he said, I'm Marsh Cuttino. A little bit about my background so you know why I'm talking to you. He mentioned a little bit of it. I am board certified emergency medicine physician. I still work extensive clinical shifts. My last shift was last night. My experience with space started at the Kennedy Space Center back in 1995. I worked at launch and landing operations between 1995 and 1999. My last flight operation was John Glenn's return to space. Did training at NASA Johnson in 98. I have been doing microgravity research for over 20 years and have extensive experience primarily with biomedical research. I have won a fair number of NASA STTR and flight opportunity grants. I have had some of my experiments go to space suborbitally. I've not yet put anything on cases, although I have looked into some of that. I'm a senior FAA aviation medical examiner, and as he said, I have founded Orbital Medicine as a research and consulting corporation, and I have been hired by Zero-G Corporation to operate as their flight surgeon. I have been working with Zero-G primarily as a research reviewer and safety biomedical reviewer for a number of years and have progressed with the flight surgeon.
Yeah, just to be clear, you're not actually speaking from inside the aircraft, right?
No, I am not. So that's just, I took this photo last weekend. I was like, I'm going to use this as my background. So wanted to talk a little bit about parabolic flight and why it's such a good analog for space. Several people have talked about how it's a good analog, and the reason it's a good analog is because you're weightless. Now, it's a brief period of time. The original concept was developed by an aeronautical engineer and a physicist, the Habers, apparently not related from what I can tell. But in the 1950s, they were part of Operation Paperclip, came over to the United States, were working with the United States Air Force, and they felt that they could probably come up with a way to simulate some weightlessness, at least for brief periods of time. They theoretically thought that the max would be around 30 seconds. Scott Crossan, Chuck Yeager were actually some of the initial pilots tasked with developing these skills to see just how they could get up, how they could try and simulate this. And it turns out that you actually can do it, and it was effective. So the initial government operations for microgravity parabolic flight started. The US Air Force started off with F-94 fighters. And between 55 and 58, they did a series of experiments basically to demonstrate it was safe and effective and things like that. Eventually progressed to a C-131, which is a small tanker, and they modified the inside of it. And as you can see in this photo, this is an early shot of some of the Project Mercury astronauts out of November 1958. And so they're wearing some of their flight suits, and they're using this as an analog for familiarity training in this instance, so that they will understand the operational challenges of working in microgravity, which is one of the interesting things is people who've not experienced microgravity, it's super hard to kind of explain exactly what's going on. It's I've had people say, well, it's almost like being, swimming, but it's not, so being weightless is a very unique experience. Um, NASA picked up the mantle of the parabolic flights. They developed the reduced gravity office starting in 1958, and they initially converted some KC-135 tankers. Um, they flew many of those. I believe there were 3 iterations of the KC-135. I was fortunate enough to fly with NASA on the KC-135s. They later transitioned to the C9 and eventually transitioned to the 727-200 series, which is still the type of plane used by Zero G. In Russia, they began using the Aleutians, so they will fly that in Russia. And in the ESA, starting in 1984, they did a series of different planes. It started with the Caravel. They tried the Aleutian for a bit, and then eventually ESA was flying the A300s and A310s, which confusingly is also called Zero G. Although I am not connected with the ESA Zero G, I am connected with the commercial Zero G corporation founded in 2004 here in Virginia. So that's a brief history of the parabolic space flight. Now, my kids are always like, explain to me like I'm 5. So how does this actual parabolic flight thing work, and how does it make zero gravity? So what we're doing in this, it's technically an acrobatic flight profile. So which led to some interesting things with the founding and initial certification of this. With the FAA, initially they wanted to have everyone wear a parachute until we pointed out that, for this size aircraft, if you're wearing a parachute, you're not be able to do a whole lot. Eventually, after many years, it took almost 10 years to get the FAA clearance, we're able to demonstrate that this actual flight profile is a very stable and safe one. So it's not a high risk profile, but what we're doing, we're starting around 24 to 25,000 feet. And we start with a pull up, and you're pulling up about 45 degrees. And as you're pulling up, the engines are cranked up and you start feeling weight due to the acceleration, and you end up getting around 1.8 Gs. So you're weighing almost twice of what you normally weigh. And then you're going to get right up to the top. And it's actually before you get to the top that you start going into the free fall. And what's happening is the plane, and everything in the plane are falling at the same rate. And the pilot, in a very careful maneuver, is aiming down so that he is going down at negative 9.8 meters per second, which is able to give you the rate that the plane is going down at the same rate that you are falling, and thus producing about 20 to 30 seconds of zero gravity time. So it's from the start of going up and then you're going over. One of the best descriptions I've had of it is people say right when you go over the top of that roller coaster, you are weightless for just a second. This sort of just stretches that out. And so that's how you're actually producing this weightless period. All right, so we're able to do this, and we're able to develop high quality microgravity. It occasionally is a little weather dependent. So if it's a little windy up there, sometimes it's a little shorter, sometimes it's been longer. As far as I'm aware, longest parabola was around 45 seconds. So that was some good hang time. One of the nice things about using parabolic flight is when you get down to the cost of weightlessness, this is the cheapest way to get weightless. So it's several orders of magnitude easier to get into a parabolic aircraft than it is to get your experiment flown suborbitally or orbitally. So it is very frequently used as a pathfinder for a lot of these research and training operations. So before you actually pack everything up and go to the International Space Station, it's much easier to go and do a zero gravity campaign so you understand what's going on. There's a long history of parabolic research programs and commercial tourist operations with Zero G Corporation. Over 1,500 people have flown on Zero G since 2004. So we have provided weightlessness for more people than any other provider in the world. It's an incredibly useful tool to eliminate gravity, which for a lot of things is just fascinating. You know, the core part of science is changing something. and seeing what makes it happen when things change. And so by pulling out gravity, we're able to study medical and biological processes. We're able to see how humans operate and change in it. So you can use it for human factors trainings, fluid dynamics, very robust and interesting field, mixing, fascinating field, and phase separation, where a lot of my personal research has been done, is just an extremely interesting, things just don't act the way you expect them to. Heat transfer and combustion, also very robust things that you can learn a lot about on a parabolic flight program. So it is a very nice, easy way to get a lot of stuff done. And there's a little shot of our plane right there, G-Force One, the 727-200. Several people have mentioned Inspiration 4. I would just like to point out that Inspiration 4 got their microgravity orientation, so they knew what to expect on 0G. We are also, there's going to be some other commercial flights. Axiom is going to be flying some astronauts to the commercial space to the International Space Station as preliminary commercial space station development. So they have also had some training. And we are also have been used for other things such as movie films. The original Matrix was filmed in parabolic flight. And a lot of different movies, TV shows, and other things have also used the microgravity experience to have unique and exotic videos. So of course, the reason I'm actually here is, some of the medical considerations. And for those of you who don't know, the old nickname for especially the KC-135 was called the vomit comet. When you go back to the early NASA flights, it would up to a third to a half of people would get sick on the vomit comet, which led to a lot of research into motion sickness. There's a lot of changes that happen in the flight environment, including air pressure, vibration, temperature, and gravity. Obviously, the gravity change is the reason we're up there, and you get a fair number of physiologic changes as well. So I'm going to go a little bit more detail on those. Motion sickness is that feeling of nausea, disorientation, unsteadiness that you get. It tends to happen when you move too fast, and it's related to motion. Now, it's a syndrome of the autonomic nervous system, and you get a lot of gastrointestinal changes. And when you get the gastrointestinal changes, you get what we call an emetic effect, which means you throw up. So as it's recurring in response to motion, you have to have the motion to trigger it. If you don't have the motion, you don't trigger it. But it's interesting because there's a significant variability among individuals and what precipitates it. You'll see some people who get sick on roller coasters, some people get sick in cars, some people get sick in planes. But just because you get sick on a plane doesn't mean you're going to get sick on a roller coaster. Just because you get sick on a roller coaster doesn't mean you're going to get sick in 0G. So it's a lot of preparation and things can help you avoid it. Adaptation occurs. So if you've done it for a number of times, you tend to be more tolerant of it. And the best way to avoid motion sickness is to not move too fast. So if I'm going to reinforce anything for all you guys who want to get on there and fly with us, what we're going to talk about is like the first thing you don't want to do is when you get wasteless is bounce around and go flipping and flopping because that gets your otoliths twisting and turning. And what happens is your body starts thinking, hey, I'm not like stable, and it triggers what we call the neurotoxin expulsion and avoidance system. So your body actually starts thinking something here is poisoning me. I need to not do this. And that makes you vomit because the body thinks that you've ingested something which is causing a neurotoxin. And so the body's first reaction is, I need to get that toxin out of there. So I've had a lot of people ask me evolutionarily, why would we have this problem with motion sickness? And it's actually a maladaptive response. So the body thinks you're getting poisoned. And so that's actually why we do it. Now, we have things that we can do. We can do scopolamine patches. It turns out Zofran doesn't work so well, but things like Compazine will work a little better. So we have medications that we can use. We've gotten better over the years just with training. So just like being aware of how you're flying, your orientation and things like that, you can reduce the risk of getting sick. And so we have significantly reduced over the years the incidence of sickness. It's not zero, but it's less than a 5 to 10% nausea rate on flights. We have a significant number that no one gets sick. So it's gotten better over the years. It's not really the vomit comet anymore. And we've developed a significant understanding of what a lot of the problems are that go into this nausea. It's been interesting. There's been a lot of concern. Are you going to get the same sort of thing in the suborbital flights? It is a single big parabola if you look at it that way. And I think there's still going to be a lot to learn with that. This does feed directly into space motion sickness, where a lot of the astronauts will get ill from bouncing around on the inside. And it's the disconnection between the sensory balance system in the brain and what the visual and body is actually feeling. A little bit about the flight environment itself. It's a novel environment. Your gravity levels are alternating between 1.8 and weightless. We will also do lunar and Martian levels. So one of the things we've discovered, if we start off with a couple of Martian parabolas, so you experience what it's like to be on Mars, then a couple of lunar before the first 0G, the body adapts with these altered levels of gravity and actually does much better going into the weightless parabolas. The cabin pressure is a little bit lower in the aircraft. It is a standard, it's around 2,400 meters or 7,900 foot air pressure, but that is a little drier than most people. There is a fair amount of vibration because the engines are running, so it's a low vibration. It's got a frequency 1 to 400 hertz, but it is there. And it's a low humidity because of the coolness of the air. A lot of the moisture just gets sucked out of the air, so people get a little bit dry, and it's noisy. What you're seeing on the screen there is a shot of a continuous decibel meter. You've got just the start of one of the high G pull-ups. So we're going from 0G right at the edge, and you see the little marker there, and they're flipping as it goes into the high G pull-up. And so what most of that noise is engine noise. You get a few physiologic changes when you're in the parabolic flight. Because the duration is shorter, it tends not to be as extreme as a lot of the long-term space flight. Most of the physiologic changes are basically because of the cabin, because it's low pressure, low moisture, and you look at a little bit low oxygen. So because you're at a little bit of an elevated air pressure, surface level, the air pressure is lower. And as the air pressure gets lower, you get some lung changes. Your baroreceptor sensitivity is reduced. You get some increasing variability in your blood pressure. And a lot of times it'll start going high in the beginning and then decline towards normal by the end. Your systemic vascular resistance changes, and it changes based on the gravity level. Your heart's trying to pump against gravity. And when you get weightless, it all kind of pushes to your brain. And one of the things with the rapid alternating gravity levels is you get increased hormonal releases. A lot of the gastric and stress hormones gets released. People who get motion sickness will have really extreme hormonal releases. So that can contribute to the motion sickness. And if you have a random sample and are looking at people's gastric hormones after, you can look at that and figure out exactly who's got sick and who didn't. Want to just touch a little bit about research. A lot of the research is obviously proprietary, so I can't show you a lot of pictures of research, but this happens to be one of the projects I'm a co-PI on. A lot of the biomedical research, this is a research project. It's a joint project between Purdue University, University of Kentucky, and myself, Orbital Medicine. We're developing a fully operational surgical suite. This is going to be flown on Virgin Galactic in the next year or so. And we have the capabilities to do suction. We can do an appendix. We can do a laceration repair. We can fix a bleeder. We can do a whole bunch, gallbladder, whole bunch of stuff. So we're going to basically have this full set for both training and treatments. And it's eventually going to be flown to the International Space Station further down the road. Quick overview, sort of thoughts of when you are wanting to do research. I figure there's probably at least a fair number of researchers watching this, not just people who want to go for fun and tourism. The biggest issues are going to be logistics and coordination and just getting everything down. If you're setting up a big campaign, collaboration is always very important. You want to make sure your flight test planning is robust, have a good hazard analysis. Got to make sure everyone is healthy enough to get on. We're expanding who can fly. And there are things going on to expand who can fly to space as well. But it still helps to have, for example, an aerospace medicine trained physician involved in some of these projects, especially if it's going to be complex. If you're working on humans, you got to make sure you have your institutional review board. And I'm talking more about American-based research here. There are other equivalent organizations for the Far East, Europe, and things like that. One of the biggest things to consider is your experiment design. It's got to be something that you can do in zero gravity. It's hard to explain some of the pitfalls that can happen if your experiment is designed poorly, but you can have things go sideways if you've not realized it. One of the famous things I remember talking about, there was a guy and they thought it was a pole. It was in the middle of experiment. There's a bunch of fluids in the bottom and it was coming out, and it was turns out it was actually a vent, and in zero gravity, all the fluid just came out and went up into the cabin. So we had to shut that experiment down. So recognizing that fluids and things do not go the way you expect in zero gravity is part of the learning process, but it's also while you're there. So, but people who've done this before can point you in a direction for pitfalls and preparation. When you actually get there, payload processing, you'll work with your flight provider, whether it's Zero G, Blue Origin, Virgin Galactic, SpaceX, NASA, and work to getting your payload ready. And then you want to get your data out, and then you got to figure out how to adjust anything. Environmental consideration is going to be the last consideration when you're doing this. And, have at least one learning plan and then go from there. All right, I know that we're short on time. This was a 20-minute talk, so I want to thank everybody for allowing me to participate. I think this is a very interesting conference. I've enjoyed watching and learning along with everyone else, and look forward to the rest of the day.
Thank you, Marsh. I'm always amused to think that they had a Scopedex patch on Young and Crippen for STS1, and then you look at the bottle for scopolamine. It says, "Do not operate heavy machinery under the influence of this drug."
Yes. So, of course, they had the flight surgeons to help them out, but yeah, there was the space motion sickness and the vomiting early on. It can be very disruptive to mission success.
So, and we'll talk about that more during the panel, I think.